Okay, we still have a bit part about the spanning. Okay, turn to page 169. Don't forget to like the video or love the video so I can see that you are there. I can see 17 of you already like. Okay, page 169, definition 3.5. Okay, S spans V. You remember the diagram that we have earlier? V is the whole vector space, and there are 4 types of vector space. It's either, what are the 4 types of vector space? It's either Rn, matrices, polynomial, and function. Okay, we don't have any other vector space, just these 4 for this class. And S is just a finite subset of V. So this is a subset of V. V is infinite. Okay, V is infinite because you cannot count how many. There are infinitely many. S is just a subset and finite. So let S be a set or subset of V that consists of a finite number of vectors. Okay, a vector space V, whatever inside the elements, we call it vectors, right? Let S be a set that consists of a finite number of vectors in a vector space V. So let S be a set of a vector space V that consists of a finite number of vectors. Then S spans V, or V is spanned by S if span of S is equal to V. So span of S is infinite. You remember span of S, if S is V1, V2 until Vk, okay, span of S is just the linear combination. So if you take any linear combination of all the vectors in S, V1, V2 up until Vk, the span is infinite. If these are equal, then we say S spans V, or span of S equal to V, if they are equal. Sometimes span of S is just a subset. Okay. Sometimes we have seen in our class earlier that span of S is not equal to the whole vector space. So in that case, we say that S does not span V, or we say that V is not spanned by S. Okay, so it's all about the spanning. So in short, I can say that this is very important. S spans V if every vectors in V can be written as a linear combination of the vectors in S. S spans V if every vectors in V can be written as a linear combination of the vectors in S, meaning you can find the C's. Okay, let me write what it means symbolically. Okay, that is, if S is V1, V2, Vk in V and Y in V, then there exists C1, C2 up until Ck in R such that Y equal C1 V1 plus C2 V2 plus Cn Vn. So you see that this is back to the linear combination. Okay, the difference is this is for every. So before this we put numbers. Now we put just as any variables. If it is in R2, you will put Y, sorry, call it different, W as XY, and then you solve. Okay, we will see by this definition S spans V if for every vectors in V can be written as a linear combination. This is the key word. Okay, this is chapter 2. When you solve the equation, whether the system is consistent or not. So this is just chapter 2. Okay, let's try. Before that, okay, there are theorems. You just use this theorem to know whether it's span or not, but you cannot just mention because of the theorem then it span or it does not span. Okay, I will explain when I explain the theorem. Theorem 3.2. Okay. All right, suppose U1, U2, Um is in Rn. Okay, see, just now I used K, but now we use M. There are M of them in Rn. Okay. If M is less than N, then S does not span Rn. I'm saying this again. If you need to prove whether a subset S span or not the vector space, you need to use the definition, meaning that is a linear combination or not. But this theorem gives you the answer ahead. Okay, but you cannot say since 2 is less than 3 does not span. No, you have to show it by definition. Okay, what does it mean? This means if the number in the set, number of vectors in the set is less than the dimension of the vector space, it does not span. It's not enough to span. You have seen this example before. S equal, say like this, right? Okay. Now you tell me what is M and what is N. is m in here? N, what is n in here? Can you type? Okay. M is the number of vectors in this set. How many vectors in here? Just one. Just one. N. N is the dimension. N, this is in R2 because there are two components. So, N is 2. Okay? Another example. What is the M and what is the N? For this one? Okay. M is the number of vector. Okay, M is 2, N is 3, because this is in R3. Okay, so in these two cases, S does not span R2 and S does not span R3 by this theorem. Okay, this is just to check whether it spans or not. But how do you write the answer? Okay, this is how you write the answer. Okay, so the question is, does S span V? Okay, so let Y be XY. Okay, I will write this here. Y erase. Okay. Oh, this is bad. Because if I use XY, I cannot use Y. So find another like U. U. Okay. Okay. So just now we said that S spans V if every vector in V can be written as a linear combination of vector in S. Okay. Now, S span R2 if any vector in R2 which is XY can be written as, okay, then U is XY equal, but there is only one. So your C1, C2, there is only one. Okay. Can you write this equation for all XY? Can you find C for all XY? So how do you solve this? If you want to solve by you will put C equal X, right? C equal X, 2C equal Y. You cannot really see, right, whether there is a solution or not. You cannot really see. But if you write this as 1, 2, X, Y. Okay, 1, 2, X and Y. Then row reduce. Negative 2 R1 plus R2, 0. Okay. Negative 2 R1 plus R2, negative 2X plus Y. By solving this, you cannot really see what's happening. What is C? C from here is X. C from here is Y over 2. Then you will say there is a solution. But this is only for one particular value. But if you write like this, 1, 2, this one becomes the xy, okay, and then you row reduce, you will see that this is inconsistent because the rank is 1, the rank of the whole thing is 2. So inconsistent meaning there is no solution, meaning C does not exist, meaning you cannot write all U in R2 as a linear combination of vectors in S, so S does not span V. Okay, so the key is to solve this equation. Okay, if you want to see it this way, 1, 2 is just this. So the span of 1, 2 is just this line. Okay, C times 1, 2 is just this line. So there are many vectors outside here which is not in the span. So the span is just a line, it's not R2. Okay, so in that sense, it does not span for that one. But there is also the next question. The next question, what is the span? Okay. So does S span V? No. Right? What is, this is the next question. What is span S? Okay. This is quite tricky. How do you find span S? Okay. But since you have done this, it's much easier. That span S is this, but you have to do equal to 0, right? So span S is xy because it's part of R2, so it is xy, negative 2x plus y is 0. Then you write, this means what? X, 2x, right? X in R. So you just take this equal to 0, y is 2x, so you can just write this. This is this line. Okay, that's also in the exercise. If you tell me that the span is the line y equal to x, I will also accept that. This is another way to write it. Okay, so this is for that particular theorem. There's another one. The question number 2. Okay, is this one. S is 1, 1, 3, 1, 2, 0. Okay, question, does S span V? So from here you know V is R 1, 2, 3. Okay, then we do the same thing as before. From the theorem we already know, this is just to check, this is not part of the answer. To check, you will say that M is 2, N is 3, so 2 is less than 3, so you know the answer is does not span. But you cannot just state N is 3 because you didn't prove the theorem, we just used to check. So does S span V? If you just answer since 2 is less than 3 does not span, you don't get any marks. Okay, so S spans V if for all, this is for all U in V that exists C1, C2 in R. This means for all U in V that exists C1, C2 in R. This is such that for all that exists such that. Why there's only 2? Because there's only 2. Okay, so U is X, Y, Z equal C1 113 plus C2 120. So back to the previous section of linear combination. Okay, so solve this equation. Back to chapter 2. If you remember again, how we write this in chapter 2 is to put this, but instead of putting numbers at the last column, we put now X, Y, Z. You see from the question, they don't give you X, Y, Z, they don't give you the C, so you have to come out with this, because if you answer your test or final, this has marks, whether you know the definition and whether you know how to write as a linear combination. So again, this one needs row operation. Negative R1 plus R2, negative 3R1 plus R3. Okay, so 1 X, negative R1 plus R2. Okay, be careful with this, because now it's not numbers, it is variable. So you just have to do it in terms of X and Y. Negative row 1 plus row 2. Negative 1 and add. Negative 1 and add. Negative X plus Y. This one is negative 3R1 plus R3. Negative 3 and add. Negative 3X plus Z. Okay. Now you want to make this 0. So 3R2 plus R3. Right. So the last one will be 1 X 0 1 negative X plus Y 0 0 3 and add. Just do it in your kertas conteng ke apa ya. You add, you multiply this with 3, multiply with 3 and add. So negative 3x add with negative 3x, negative 6x. Okay, and then you have plus 3y plus z. Or you can put like this, 3 plus, kata conteng ya. So negative 3x plus negative 3x is negative 6x plus 3y plus z. Okay. Now this gives the rank 2, the rank 3. Or you see 0 equal non-zero. So the system is inconsistent. The system is inconsistent. So there does not exist C1, C2. Okay, you have to write in full if you don't know the symbol. The system is inconsistent, meaning there does not exist C1 and C2 for this one. So answer, sometimes student forgot to answer, S does not span B. Okay, so in the case when M is always less than N, and then for Rn only, yeah, for Rn only, then you have this case. Okay, now we go to the next case. If you realize it's only Rn, this theorem only applies to Rn. It does not apply to polynomial, matrices, and function. Okay. The second one is when M is equal to N. The second one is when S is U1 U2, UM, Rn, and M equal N. Okay, if you remember in chapter 2, when you have M equals to N, when you do the matrix, you get a square matrix when M is equal to N. Okay, so how do I write this? Okay, let A matrix, yeah, U1, U2, UM. So every single U you write as a column vector. So A turns out to be M by M because they are equal, right? There are M of them. Each one is in Rn. Okay, like there are 3 in R3. Okay, so you will get a square. Either you call it M by M or N by N. If A, the determinant is not 0, then S span Rn. If the determinant is 0, then S does not span Rn. Okay. If you look at page 3, system of linear equation, if you look at the 3 diagram, this, okay, the case when M is N, this one, yeah, the case when M is N, and about the determinant, right? Okay, now I have done example 314 number 1 because this is very similar to the one before, but just now I did not finish the last part. The last part when we have the equation of x, y, and z. So I erase this. So if the question before asking what is the span is when you get that equation at the end equal to 0, then that is the span. Okay, let me rewrite. I'm not gonna copy again because it's there, just to explain. 3.14. You don't have to copy because it's done. So S equal 1, 1, 2, 2, 1, 3. Okay. Now, even if you are not given the V, you will know to write this is R 1, 2, 3. Okay. And you see there are only 2, so M is 2, N is 3, so you know it does not span. But the question is what? Okay, there are 2 parts of the question. First one, does S span R3? If the answer is yes, meaning span of S is the whole of R3. If S does not span what is span of S? Okay, so you have a 3-dimension and you have 2 vectors. You know that it will span a plane. Okay, a plane. But what is the span? So look at the notes, page 170. Okay, this is 112, 213, X, Y, Z. Okay, you will get 1, 2, X. I make it 1 here. And 0, 0. Okay, 1 more. So this is row echelon matrix. Make this 1. Make this 1 means this is X minus Y. Now, this is inconsistent, so S does not span R3. Oops. S does not span R3. But what is the span? Span of S is, it has to be in R3, so X, Y, Z in R3, such that this equal to 0. Okay, just checking whether this is clear enough. This actually is a plane. You just leave your answer like this, is okay. But this is actually an equation of a plane in X, Y, Z, right? Okay. Move on to number 2. Okay, so we go back to the case M equals to N, because this one I didn't finish before, so I show you the spanning. Now to go to the second case, okay, S equal 1, 1, 1, 1, 2, 1, 2, 0, 0. Okay, you see, M is 3 and N is also 3. M is 3, N is also 3. Then you just have to find actually the determinant and you check whether it's equal to 0 or not. From there, I'm not gonna calculate this again, but this is not 0. Okay, you cannot just say, okay, the determinant is not 0, so it's span. No, because you have to write in terms of the definition. So S spans V if for every X, Y, Z in R3 there exists C1, C2, C3 in R. Oops, sorry. 1, 2, 3. Such that X, Y, Z can be written as C1, 1, 1, 1 plus C2, 1, 2, 1 plus C3, 2, 0, 0. This gives 1, 1, 1, 1, 2, 1, 2, 0, 0, X, Y, Z. Okay, so back to chapter 2. Okay, back to chapter 2. You can solve this with Gauss-Jordan, or you can use any method. Okay, but we have calculated the determinant. Okay, then you can say that since the determinant of A is not 0, then the system is consistent. Okay, see, they exist. So C1, C2, C3 exists. So what does it mean? S span V. What does it mean by S span V? What is span S? Span S is V. Okay, meaning if you take this vector, you take the linear combination, you will get the whole of R3. The whole of the R3. And if you give me any number at all, you can find actually X, Y, Z in linear combination of these three. Okay, since you don't use the row operation, okay, you don't solve for C1, C2, C3. If I want you to write a linear combination of any vectors in V, then you have to calculate again. Okay, because if you ask me why you don't use the row operation, if the question is just to see whether it spans or not, this is okay. But if the question asks, maybe the next question is write like 2, 3, 6 as a linear combination of the vectors in S. Okay, write 2, 3, 6 as a linear combination of the vectors in S. Now you have to redo this because you haven't done any here. So what you will do is just to put in 2, 3, 6 here. Okay. In the notes, I did do this, calculate. Okay, there's a shortcut, there's a long one. 1, 1, 2, 0, 1, negative 2, 0, 0, 1. So this is only until row echelon form. This is x, negative x plus y. What is that? Negative x plus z over 2. Okay, so you can also reduce this, and this means the rank is 3, the rank is 3, the solution is unique, consistent, that's why it's span, and the span is R3. So if I ask you again what is this as a linear combination, it's easy, because you just put in 2, 3, 6 in here, you will get Z, and then you can solve. Okay, then you can get C1, C2, C3, and then you will get the linear combination. So it depends on the question, whether the question want you just the span or they want you to write as a linear combination. Okay, now number 3 on page 172, why it does not span. So I change this little bit, same question, okay, same question, but a different vector. Okay, I have no update yet for your test 2. We put it in week 12, I think. Now we are in week 7. Okay, but test 2 covers the whole of chapter 3. Okay, and we haven't decided how we are going to do test 2. Okay, so if you check this, although I said only chapter 3, but you have to know chapter 1 and chapter 2. So it's actually chapter 1 to 3, although the question is in vector space. Because you see, just now you do row operation, now you're doing the determinant. Right? So if you calculate this in any way, you'll get this equal to 0. So by the theorem, you know that S does not span. But the question then is, what is the span? If it does not span, what is the span? Okay? If it span, then it's the whole vector. Right? So again, I give you this. Okay? You need to redo this. Don't just read, don't just look. Take this and then redo until you get the same answer. If there is a typo, let me know. Yeah? Okay, row echelon form. Okay, you will see the rank is 2, the rank is 3. So this is inconsistent. So S does not span V. But what is span S? Span of S is 3 of them, X, Y, Z. Just take this equal to 0. So this is also a plane. Okay. Over there you will see the word basis, but forget about that for now, because basis comes after this. Okay. Alright. So all the basis will come after. We will go back and we'll mention about the basis. Okay, so example number 4. Okay, so I increase the dimension, but still in this case m is less than n. Okay, so m is 3 and this is in R4. 1, 2, 3, 4. So again, you know it does not span, but you need to see the spanning. So you will put X, Y, Z, W. Why X, Y, Z, W? Depends. You can put W, X, Y, Z. You can put X1, X2, X3, X4. Okay. So quite a long calculation to get to the end. Okay, make sure you know how to get to the end. Okay, this is just row operation. At the end, you will get 1, 2, 1, X, 0, 1, 2, X minus Y plus Z, 0, 0, 1, X minus 2Y minus 3Z plus W. So you have to be very careful when you're doing with X, Y, Z. Okay, and the row operation. Because if you don't do this right, if you don't double check, then your spanning set will be wrong. So this is X, Y, Z, W, negative X plus 2Y minus 3Z plus W equal 0. After this, there's another question. What is the basis of the span? Okay, but that is later. Okay, let's look. Okay, now I have only two cases. Okay, I have only two cases. If you remember, I have the case m less than n. Okay, and then I have the case m equal n. What happened when m bigger than n? Does S span V? Yes or no? Okay. Write your answer, yes or no. Everyone, type yes or no. If m is bigger than n, meaning the number u1, u2 until um in Rn, if this number is bigger than this, does S span V? Yes or no? Cast your vote. Anybody want to answer that? Okay, one no, one yes. Nick says no. Aizatul says no. Shun, yes, yes. Some more. Yes, Shafika. Chai Ying say yes. Yes again, yes. Yes. Wow, so many yes. 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 So the case is when m is bigger than n. This case. Yes. Nobody said no. Ni tembak aja yes or no, or you think. Okay, I give you a very simple question. S is 1 1, oops, 2 2, 3 3. What is V? V is R2, right? Because 2 component. What is M? So M is 1 2 3. N is 2. M is bigger than n. Okay, this is the case. Now the question is, does S span V? You guess, you think. Okay, so if you thinking about it geometrically, you think about it geometrically, 1 1 is here, 2 2 is here, 3 3 is here. Spanning is just a linear combination, meaning you multiply any of these two. Okay, you add, then you multiply, and so on. Even if you add, you will get only this, right? The spanning also just the line, so you don't get the whole xy, meaning this does not span. So the answer is no in this case. Does not span. If you put this 1 1, 2 2, 3 3, xy, what do you get? You will get 1 2 3 x. negative R1 plus R2, right? 0, 0, 0, negative x plus y. So span of S is xy, because it's R2, negative x plus y is 0. This is not equal to R2. So this is just equal to x. So that's why I said it's just that line. Span S is just this line. So S does not span R2. Yes, so it depends on the question. Okay, so all of you are right. The answer is either yes or no, depending on the question. Because I can give another example that it does span. Okay, so for this one you understand, yeah? Because they are just multiple of the other one. Okay, so when you do this, you see that this is inconsistent. So in this case, you don't need these two. Even if you erase these two, then you still get that line. So there is no use of these two. So in our next section, they will ask what is the basis. The basis is just the column that has the leading one, which is just one vector. So you will say this is the basis. Because you don't need these two. They will just give you the same line. Okay? But if I change this, call it as prime 1, 1, 1, 2, 3, 3. Okay. Still, V is R2. Still, M is 3. Okay, and still, N is 2. M is bigger than N. But then, in this case, the answer is yes. The answer is yes. It spans because you don't need this one, because this is a multiple of this. You don't need this. You just throw this away, right? This already spans because the determinant is not 0. But if you want to look at this way, you will write, Brian mentioned about the many solution, which is also true in this case. Okay, so negative R1 plus R2, 1, 1, 3, 0, 1, 0, negative x plus y. So in this case, you have a free variable which is C3. Okay, so the system is consistent, right? The rank is 2, the rank is 2. The system is consistent. Thus, the C1 exists, right? XY in terms of C1, C2, C3. Thus, S spans V. So in this case, yes. Meaning, span S equal R2. Okay? Just these two will span the whole R2. Any combination, oh sorry, here. Any combination of two vectors, any combination of two vectors in R2 which is not parallel, okay, they will give determinant not 0. They will span the whole space. So if I draw, I said again, if you have x and y axis, if you have any vector that has an angle, if they are parallel or they are on the same line, they don't have a angle, they span the whole space. So if you have additional vectors, they will also part of this linear combination. Alright? So to answer, the answer would be yes. It can be yes, it can be no. Alright, so it depends on the question. So this theorem can only be used when it is equal or when it is less than. Less than means not enough to spend, so it does not spend. Equal, it depends whether even is equal, it is multiple, or it is not. Okay. Now, I mentioned earlier that the theorem only applies to Rn. Okay. Now, I want to extend to P and to matrices. Okay. So, vector space. Number one is Rn. Okay, Rn is n, and for m by n, you will look at m times n. Okay, let me give you an example after this. If it is Pn, okay, so I will put n here, I will put m by n here, I will put here n plus 1. Because for polynomial, you start with x to the 0 until x to the n. So you actually have n plus 1. Okay, let me give you example. Just now, we say that m is 2, n is 2. Okay. For matrices, this is one example. Okay, one here, one here, one here, one here. 2 by 2 matrix. Okay, this is 2 by 2 matrix. So I need to have 2 times 2 to be equal. 1, 2, 3, 4 is 2 by 2. If you have 3 by 2 matrix, you have to have 6 of them. Okay, that is how you count the m and the n. So this one, m is 4, n is also 4. That is how you count the n in the theorem. For this one, 1 plus t, 1 plus t squared, something like this. So in this case, m is 3, n is this plus 1. Okay, n plus 1. Okay, this is P2, right? This is P2. This n is the highest power, the degree of the polynomial, adding 1. That is your n in the theorem. Okay. And to see whether this span or not, this is more complex, but remember the one that we do linear combination last time, this can be also changed to in terms of Rn, right? You remember last time we saw for matrices, we also write as down, write as a column. So it is the same. Before, okay, let me, so I skip all the last sentence of basis, yeah, because we are not doing basis yet. We will go back to the example after I define basis. Okay, look at number 7. Okay, look at number 7. S is 1 1 0 0 1 0 0 0 0 1 0 0 1 1 0 1. Okay, so if you look, m equals 4. the n in the theorem also equals 4. 2 times 2. Okay, so you don't know whether it's span or not until you find the linear combination and the C. So what we do before is just write this out, because this definition give a mark. That is part of your jalan kerja, right? S spans V if for all, we call it A, B, C, D. I call that W, X, Y, Z. W, X, Y, Z. W, X, Y, Z in that exists C1, C2, C3, C4 in R, such that, okay, C1 plus C2 plus C3 plus C4 equal. Okay, this is very important, because this is how you will get your linear equation. If you don't write this out, I wouldn't know what kind of variable that you use, the C1s or the W. When you do this, after you write this, then you multiply out, you add, you equate, then back to chapter 2, right? We can write 1, 1, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, and then W, X, Y, Z. I think this is quite easy because there's so many ones and zeros. You just need maybe 1 or 2. Okay, I will write the last one. It's in the book. 1, 1, 0, 1, W, 0, 1, negative 1, 0, X minus Y, 0, 0, 0, 1, W, 0, 0, 0, 0, Z. Okay. Okay, so you see, the rank is 3, but the rank of the whole thing is 4. So there is no solution. The system is inconsistent, meaning S does not span V. Okay, so what is the span? It's a little bit tricky. Okay, from the last one, okay, I erase this first. So S does not span this. Okay, because this is inconsistent. So you have to write it up. The system is inconsistent, C1, C2, C3 does not exist, so it does not span. What is the span? Span S, this is quite tricky because you have to know what your vector space is. Now, span S, S is in terms of matrices. So you have to write in terms of W, X, Y, Z, sorry, in terms of matrices. What is the condition? The condition is here, right? Z is 0. This is the problem here. z is 0. Okay, what happens when z is 0? So you just put in w, x, y, 0. Okay, so w, x, y in R. Oh, sorry, w, x, y, z. Okay. This is wrong. This is wrong. This is x, y, z, w. Okay, we do consistent like the book, yeah? X, y, z, w. So at the end, I changed a little bit, but it's actually very similar. Let me just follow the book so you don't get confused, yeah? X. Okay. So x minus y, w and z. Okay, I change this. Following this, x, y, z, w. Okay, z is 0. So this gives x, y, 0, w. Okay, x, y, w in R. Okay, so now it is equal. Okay, and the one that I do this is the basis, 3 of them. Meaning you can never get the whole matrices because you will never get the third component to be a number because all third component is 0. Okay, so it does not span the whole of the vector space. Okay, last one would be number 9, the polynomial. Yeah, I just see that x, y, w, z. This is okay, yeah? Alright. As long as you are consistent, you can use w, x, y, z, you can use x, y, z, w, you can use x1, x2, x3, x4. Okay, now number 9. Okay, s equal 2 plus x 1 minus x squared. Now if they don't give you what v is, this is the highest degree, so v is p2. Okay, m is 2 and n is this plus 1. Okay, you remember the third case, polynomial is n plus 1. Okay, so s spans, okay, p2 if for all, what is the polynomial? Px equal a not x, oops, plus a not x plus a squared. You know, any polynomial in Pn is in this form. Px is, we normally write this way, right? Okay, this is in general. Any polynomial with degree n can be written as this form. Okay, the coefficient you can change, but I write the coefficient a, you can put c, but because our the linear combination using C, so I don't want to use C. This one is different because the question is the other way around. The question is increasing degree. Normally it's decreasing degree. So for polynomial, this is your vector y. That for any vector y in V can be written as a linear combination. So you have to know your general form of your vector in the vector space. So for my Px in this whole vector space, P2 is in this form: A0 plus A1x plus A2x squared. Now, sometimes the question use T, so you have to follow 1 plus T, T squared, and so on. Okay. Now, next one is, I haven't finished if for all Px there exists C1, C2, only 2 in R, such that this is in terms of C1 times 2 plus x plus C2 times 1 minus x squared. So when you see this, you will think that this is too complicated, but actually this is very similar to the case of Rn, okay, that we did before. We have done this in linear combination. So although it looks complicated, but this is just like Rn. R3. How do you solve this? So you can multiply and so on, but last time, if you remember, I said this is to the 0, right? This is to the 1, this is to the 2. So you just write as column 2, 1, 0, right? 2, 1, 0. For this one, 1. There is no x, negative 1. Okay? Suddenly I'm so hot. Okay. 2, 1, 0, 1, 0, negative 1. Okay, 2 of them. Then this one is A0, A1, A2. That's it. Okay, that I use RST. It doesn't matter. In the book, I use RST. Okay, so you solve this. Okay, change. Okay, change row to 1, and then okay, so you just do row operation. Let me stand up. Okay, so this one is, so this one you can do negative R3, and this one you can do negative 2R1 plus R2. Okay, so 1, 0, A1. 0, negative 2 and add, negative 2 and add. Be very careful with the third one, yeah? So negative 2 A1 plus A0. Okay, and then just 0, 1. Why do I do this? Oh, because this is not yet. 0, 1, negative A2. Okay, and then negative R2 plus R3. 0, 1, negative 2a1 plus a0, 0, 0, negative r2 plus r3. So you get 2a1, wait, you start with a0, negative r2, negative a0 plus 2a1 minus a2. So the system is inconsistent, thus CI do not exist, thus S does not span V. Okay, and what is the span? Span S, now S is in terms of P2, this one, A0 plus A1x plus, oops, A2x squared, this is equal to 0. Negative a0 plus 2a1 minus a2 is 0. Okay, you can put also this is in P2 or not. In my notes, it's a little bit different because you bring everything to the right side, you get the same. Okay, you can do a0 minus 2a1 plus a2 equal 0. So that is the span. Okay. Okay, I will stop here.